Hey guys, as you can see, your midterm's coming up for this class pretty soon, believe it or not. So we're holding another review session, HKN. It's going to be Sunday, 3/6 from 2 to 5 in the HP Auditorium, 306 Soda. So show up if you want some practice.
So the other administrative thing, what Jody put up on the board over there, today is the first of several grading complaint deadlines. We talked about this at the beginning of the semester. Today's the deadline for midterm 1, project 1, and homework 1 through 5. All of those scores should have been up for at least a week. If they're not up, or if you think a score is wrong, go to the class webpage. There's a link about grading complaints, and you go there, and there's a form to fill out. The reason we have deadlines is that before we did, it used to be the day after we published the final exam scores, I would have 40 students lined up outside my door wanting to tell me about how homework 3 never got a grade. Because the grading steps are about 10 points apart, and that means 1/10 of you, which is 40 people, are going to be 1 point away from a grade step, and another 10th of you, another 40 people, are going to be 2 points away from a grade step, and so on. And that's true no matter what policies we use about grading leniently or harshly, whatever it is, 40 people are going to be 1 point away from a deadline. So today's the deadline for complaints about project 1, homework 1 through 5, midterm 1, and it says over there what to do. Okay. Our master plan for the semester is to talk about 4 programming paradigms, 2 of them at some length and the other 2 very briefly. We've been doing functional programming. We're done talking about that. It doesn't mean you're done using it, but we're done talking about it for the most part. We're going to be talking about object-oriented programming, which you've certainly heard of and have probably actually used in whatever school you were at before this one. I'd like you to try to forget that you've used object-oriented programming and really look at it with, beginner's mind, so that you can see maybe a different point of view about it from what you've seen before. Not that that other stuff is wrong, except where it is, but having more than one way of looking at it will help you understand the big picture. So the big picture is up here. This is an abstraction diagram, a little bit different from the ones you've seen before because of that dotted line partway down. The dotted line is an abstraction that takes place entirely in your mind. So there aren't any selectors or constructors associated with it. Above that dotted line is the central metaphor of object-oriented programming, which is that of multiple independent intelligent agents. So multiple, of course, means there's more than one, which is different from what's really going on inside the computer. Really, there's the one computer running your program. But we're trying not to think about that, and instead we build an abstraction in which every window in your window system is a separate entity. Every spaceship or gorilla or Pac-Man in your game program is a separate entity, and so on. Independent means that each one has its own program. Some of them may be similar to other ones, and some of them may be completely different from other ones, but each one runs independently of the other, except that they have ways of interacting with one another. So it's just like, in this room there are a lot of people, and you can, go over and tap your neighbor on the shoulder, and by doing that, you are causing that other person to get a message that you want to have some kind of interaction. But most of the time, the person you're tapping on the shoulder does whatever he or she does completely separately from what you do. And just every once in a while you interact. So that's multiple independent. Intelligent means, they know how to do stuff. So it's different from the data structures we've seen up to now. For the most part, the data is just data. It's like numbers or something. And the intelligence about how to do things is in something separate from the data, which is procedures. And here we're putting those together so that these agents have data-like aspects. They remember stuff, but also they know how to do things. So that's the metaphor. Now, in order to implement that metaphor, looking at it from a technical standpoint, there are three things we need. And that's what's right underneath the dotted line. The three things are message passing, which we talked about last week, local state, which we'll be seeing this week, and we're going to really understand better next week, and inheritance, which is the idea that some of those independent agents are a lot like other ones, and you don't want to have to program each one from scratch. Okay, you want to be able to use the behavior of one. You want to be able to say, this kind of thing is just like that kind of thing, except for the following differences. So if we have, let's say, a kind of object called a person, and there are many, many behaviors that all people share, like we talk and we walk and we eat and things like that. Then we can say, well, there's a class of professors who are people, and they do everything people can do, but they also lecture. And then there's a class of students who are just like every other people, except they have haircuts, So that's inheritance, and we'll be talking about that. What we're doing this week, this is stuff that's not in the book. The reading for this week is in the course reader. And we are implementing on top of Scheme, a kind of Scheme++, an object-oriented system in Scheme, based on Scheme. We're doing that in order to make a connection between what we're going to do next week and what you've probably done before in classes and what you'll certainly do next semester in 61B, which isn't going to look much like next week's exploration of how to make object-oriented programming actually run in Scheme. So we're starting with something that sort of uses the vocabulary that object-oriented programming uses. And then next week, we're going to see how that's actually implemented, but I'll give you a hint. It's going to turn out that once you have Lambda, object-oriented programming is just a trivial application of Lambda. And I'm saying that because there's kind of a mystique about object-oriented programming that you have to have a special object-oriented language to do it in. And you'll see that that's not true. If you have a good programming language to begin with, adding object-oriented programming on top of it is no big deal. And that's good because you should understand how things work. Right? One of the goals of this course is when we show you about a programming paradigm, we don't just want you to see how it's used, we want you to also understand a little bit about how it might be implemented. Because that makes you a better and wiser practitioner later on. Okay. There are 4 components to our object-oriented language. They're define class, instantiate, ask, and usual. Ask and usual are like selectors. Define class is like a constructor, sort of. And instantiate is actually both. Because in this language, as in most but not all object-oriented languages, we have the idea of classes and instances. So person is a class. Brian is an instance of that class. Okay? So an instance is a particular one. The class is sort of the general description of the behavior of things like that. So define class creates a class. What instantiate does is it takes a class as argument and creates an instance of that class. So from the point of view of the class, instantiate looks like a selector, but from the point of view of the instance, it looks like a constructor. Got that? So who's with me on that? Sort of. I'm seeing some sideways thumbs. So, okay, if I wanted to model us in my computer program, I would start by saying define class person, blah, blah, blah. And then I would say define Brian to be instantiate person, blah, blah, blah. Okay? So instantiate looks at the person class and sort of pulls out from that the information to make an instance, which is Brian. Okay? So instantiate doesn't make a class. It's a selector for classes, kind of. But it's a constructor for instances. All right, so let's look at some examples. Maybe that'll make things clearer. The way define class works, it's a special form, which is to say it doesn't have the standard syntax of scheme quite, and it doesn't have applicative order evaluation. And the pieces of a defined class are called clauses. And they're kind of like cond clauses. That's where we got the name. In that there's a bunch of them, but they're different from cond clauses, because cond clauses, you really only do one of them. And here we're going to actually use all of them. So actually define class, oh, sorry, first things first. If you look at the highlighted text right here in the second half of the screen, you will see that in order to use define class, we have to first load this file from the library, obj.scum, in which these things, these four things, are defined. Okay? So that's the first thing I should have said. So now, define class, it's meant to remind you of how define looks when you're defining a procedure. So if this just said define instead of define class, we would be defining a procedure named complex, and it would have formal parameters, real part and imaginary part, right? And then all this other stuff would be its body. Okay, so that's how define for procedures works. And define class has much the same structure, even though it's doing a different job. So we are defining a class named complex. It represents complex numbers. And these things are called instantiation variables, which are like arguments to the class. I'm going to start writing things down here. So we have the names class, instance, and now I've talked about instantiation variables. Oh, and I used the word clause. So to show you how an instantiation variable works, let me jump right in and make an instance of this class. So I'm going to say define C1 instantiate complex 3, 4. So C1 now represents the value 3 plus 4i. If we actually look at what C1 is, it's a procedure. That's what we're going to be talking about next week, how we do this. But it's much like the message passing approach that we saw last week, where a datum takes the form of a dispatch procedure that you call with a message and it does something or other. Okay? So what can I do with an object once I have it? Well, that depends on its methods. A method is the name of a kind of clause. So define class has a pretty small number, like half a dozen or so, kinds of clauses, and each one starts with its name. So method is a kind of clause that's in a define class. And the syntax, again, is meant to look like the syntax of lambda. So if you imagine for a moment that this says lambda, then inside these parentheses here would be the formal parameters. I'm sorry, not the lambda, I take it back, blah, 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 back up. Like define for procedures. So if this said define, we'd be defining a procedure named magnitude with no arguments, right? And this would be its body. A method is exactly like that. It is making a procedure, but it's not doing it it doesn't give it a name in the same way that define does. But we can use these this way. I can say ask, which is one of the 4 pieces that make up this implementation. And now I put an object. Ask is an ordinary procedure. So this thing, C1 here, that gets evaluated. It happens to be a variable whose value is an object, but I could have said ask, parenthesis, instantiate, blah, 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 and that would work too. And I'm going to send it the message magnitude. And magnitude doesn't require any arguments, so that's all I have to say. And it tells me 5, which is it's the square root of 3 squared plus 4 squared, right? Which is what this says to do. Right? Because real part is 3, 3 squared is 9, imaginary part is 4, 4 squared is 16, 9 plus 16 is 25, the square root of 25 is 5. And we can say ask C1 quote angle, and it's 9.927 blah, blah, blah radians. In our object system, we provide automatic messages and methods to look at the values of these variables. So I can also say ask C1 quote real part, you get the answer 3, and similarly imaginary part will tell me 4. Okay? That's just a design decision that we made. Many other object systems do things differently because there's a whole other story that you might hear about object-oriented programming that revolves around the idea of information hiding. And that story goes like this. The way you get bugs in programs is this piece of the program does something that affects the behavior of that piece of the program in ways that you didn't intend. And this and that are widely separated in the code, and so you don't catch the dependency. And to prevent that, what we do is we build a wall around each object class so that nobody else can look inside it at the values of its variables, for example, unless there's an explicit method. So when you're designing a class, you get to say exactly how somebody outside the class can interact with you. That's the right way to think about object-oriented programming if you're on a team of 5,000 programmers, writing a huge project, where it's easy for you to write code that steps on someone else's toes or vice versa. So everybody builds a wall around their thing and says how you're allowed to interact. You guys are not going to be in teams of 5,000. You're going to be in teams of 1 or 2. So that problem doesn't apply so much. And as I think I said once before, your programs are never going to get into production. You're interested in your program only as long as it doesn't work. So the goal of our language is to make debugging easier rather than to hide information. So you just automatically get ways to examine the values of every variable of every object. Yeah? Is each class acting like an interpreter? Well, only in the sense that its methods are scheme code, right? The way you actually run the program, it could be interpreted, it could be compiled, so each class could turn into, machine language. That has to do with the underlying scheme implementation. I don't know if that answered what you mean or not. Let's go on and we'll see. Other questions? Okay. Okay, so far, this example doesn't do anything that we couldn't do before. You've seen, in fact, precisely this example near the beginning of chapter 2, where a complex number was created with a real part and an imaginary part, and you had procedures called magnitude and angle that would take a complex number and do precisely these computations. So all we've done is taken something that we knew how to do already and recast it in the language of message passing. Let me just say a word about this quotation mark right here. It means what it always means, namely the thing that comes after it is the actual datum that we want to use. Generally speaking, that's how messages are going to be presented in your code. That is, when you're writing the program, you know what message you want to send an object, and you want to put that message right in your code. And the way to do that is to make it data, which is to say you quote it. But I don't want any of you developing mystical ideas about how the quotation mark is part of the idea of being a message. A message is just a word, and I could have said, ask C1 word, quote, quote real, quote minus, quote part. Whoops, I spelled it wrong, okay. Ask C1 word, quote real, quote minus, quote part, and you would say 3. All right, so don't get hung up on the quotation mark. It means what it always means in scheme. Yeah? Okay, the question is, why don't I have a method real part? And the answer is, again, in this particular object-oriented language, we automatically generate those methods for every variable of an instance. Okay? So it's just as if we had said method, open paren, real part, close paren, real part. But we provide those automatically for every variable. Okay? And we do that, again, because it makes debugging a lot simpler if they're just automatically there. We don't provide automatically methods to change the values of variables. Most OOP languages don't do either one. You have to provide methods both for looking at and for changing variables. Our choice was, we could have provided both of them automatically. We could automatically make a method called setRealPart, but we decided it should be easy to look and not quite so easy to tinker. That was our design choice. Okay. So let's move on to something more interesting, which is this counter class. And before we even look at the definition, let me show you how it works. So define C2 instantiate counter. And there are no instantiation variables. That's all I have to say. And while I'm at it, I'm going to make another one. I'll be quiet. Not interested. Thank you. Okay. So now I can ask C2 next. I'm going to. And now I'm going to do that again, and again, and again. Okay, so every time I say next, it gives me a different answer. So this shows that we're not doing functional programming, right? I call the same procedure with the same arguments, and I get a different answer each time. So we're out of the realm of functional programming, which it clearly is, and into the realm of local state. Local means that each object has its own memory. So I can ask C3, quote, next, and it starts from 1. And now I can go back to C2, and it still remembers that it was at 4, so it gives me 5. So each counter has its own separate count. That's what local state means. Okay, questions about the idea? Yeah. Okay, the question was, I can predict what C2 is going to do next. It's going to say 6. So why is it not functional? Again, the definition of functional programming is that every time you call the same procedure with the same arguments, you get the same answer. Right? There can't be any memory of past history. And what that buys you, again, is the absolute certainty that that other piece of the program isn't going to do anything that affects this piece of the program. So for example, if you want to have multi-core computers doing things in parallel, you can, let's say you're looking at a function call with 3 arguments, each of which is itself a function call. Okay? So we can take those 3 function calls and give them to 3 different processors, and we don't have to worry at all about who finishes first or any of that stuff, because they aren't interacting with each other. Whereas if we have a function call and 2 of the argument expressions are both ask C2 quote next, then we have to worry about, okay, is this one going to be 6 and that one 7, or is this one going to be 7 and that one 6? Okay? So that's why it's not functional. Other questions? Yeah. Yeah, okay, so now let's look at the way it's actually defined, which is up here. And the thing that's new is instance vars. And the way to think about instance vars is it looks kind of like a let with name-value pairs. Okay? Well, the first part of a let. It doesn't have a body. So let me write instance vars up here on the board. And I'm going to write instance variable over here. In our vocabulary list. And notice that the name instance variable is a lot like the name instantiation variable. And the ideas are very much the same also. The difference is, where does this variable get its initial value? Okay, when we create an instance, how do we know what the value of real part is, or how do we know what the value of count is? For instantiation variables, the values come from the call to instantiate. So back here, when I made the complex number C1, that's when I said what the value of real part and imaginary part should be. Okay? Whereas for the instance variable, when I instantiate counter down here, I don't say what the initial value of count is. Because every instance is going to start with the same value of count. And so I put it here in the definition of the class. Okay, does that answer your question? Okay, so initial value from the class definition, that's an instance variable. Initial value from the call to instantiate, that's an instantiation variable. And the purpose of the difference is, does every instance have the same starting value, in which case we use an instance var, or does every instance have a different starting value, in which case we use an instantiation variable? Okay? So that's one big difference here. The next big difference is this. That's an exclamation point right there. It's pronounced bang. So this is set bang. That should go on another list. Set bang is an official, built into Scheme, special form. That its notation is just like a define, the kind of define that doesn't imply an invisible lambda. So you say define name value. We say set bang name value. The difference is define creates a new variable. Set bang, the variable has to already exist. So if there weren't an instance var's count in here, then it would be an error for me to say set bang count to whatever. Right? This is what makes our objects non-functional, is the ability to change something that already exists. It's different from let, right? Let kind of serves the purpose of give this variable this value. And you may have been thinking about let in the past when it's part of a recursive procedure as if it were kind of an assignment statement to an existing variable, but it's not. Every time you run a let, it makes a new variable for each of its name value pairs. So if there was already a variable of that name, then they both exist. There are two variables with the same name and different values, and they're both around, and which one you get depends on where you are in your program. Set bang is not like that. It doesn't make a new variable. It changes one that was already there. The convention in Scheme, and again, it's not enforced by the language, it's just a convention, is that anything that changes the value of something has an exclamation point in its name, like set bang, to let you know that it's doing mutation, because that's very important. It means you're not doing functional programming. Okay, so if there aren't any exclamation points in your program, then you are doing functional programming, basically, and if there are, then you aren't. So the method next, I mean, it's not very subtle. It says, take the value of count, add 1 to it, and replace the value of count with this new value. In other words, add 1 to count and make it the new value of count. And then, when you do set bang returns the word OK. In the Scheme standard, it says the return value is unspecified. We make sure to return something useless to kind of rub in that it's unspecified. And that's why after the set bang, we have this count here. So you've actually seen things like this before with print instructions, but officially this is another new thing that we're giving you, which is up to now, the body of a procedure has pretty much always been one single expression, because a procedure can only return one value. That's still true. A procedure can only return one value. But it's possible to have more than one expression in the body of a procedure. If so, those expressions are evaluated in order. So first we do the set bang, and then we evaluate count. The value that the procedure returns is the value of the last expression. The values of all the earlier expressions are ignored. Okay? They're computed and ignored. So presumably, all but the last expression are in there to have an effect on the world, to do something, rather than to return a value, even though they all do return values. The values might be things like okay, or the value might be something that would conceivably be useful, but we're just not interested in preserving it. And then the last expression, the value that it returns, is the value that, in this case, your method next returns. Questions about that? Yeah? Can you do set bang of instantiation variables? Yes. Once the variable's there, you can treat it like any other variable. Yeah. Another question? Yeah? Right. Yeah, if you wanted to say what the initial value of the counter was, then you would make count an instantiation variable rather than an instance variable. That's exactly the difference between instantiation variables and instance variables. So our variable, the initial value is 0, but the first value returned is 1 because we do this plus count 1 thing before we return the value. Yeah? Can setbang take a procedure as a value argument? Ah, thank you, good. Remember first day of class I said over and over again in this class, people are going to say, can I use in the context of and the answer is always yes. Right? This is one of those. Yes, absolutely. The value of a variable can be any legal scheme value. Okay? It's a hard idea to get through your head that that's always true, but it's a great principle. Yeah? Yeah. Again, this particular object language gives you automatic getter methods, examination methods, for every variable. So yeah, you can say ask C2 quote count, and it'll tell you it's count. It's current count without incrementing it. Yeah? Yeah, if count were an instantiation variable, you would say instantiate, that's the verb, instantiation is a noun, instantiate counter 5, and then you would say ask counter next, or define C4 to be instantiate counter 5, and you'd say ask C4 quote next, and it would say 6. Yeah. If you wanted to, you could build a set method into your class. You could say method set count new value. New value would be the formal parameter of the method. Set bang count new count. And then people would be able to change the value of the counter on the fly. It's up to you what methods are in your object. Yeah. Can you have one class that either does or doesn't take an instantiation variable? I'm actually not sure what the answer to that is. I think not. I mean, you certainly can't have two separate defined classes for the same name. It's like defining a procedure. The one you do second is going to win. The question is, can you put rest arguments with the dot notation in a defined class? And I have no idea. We'll try it later. But don't. Okay? And a lot of times, let me say, you're going to come up with a lot of questions this week of the form, can I do the following screwy thing? And the real deep answer to that question is maybe you can and maybe you can't in this particular object language. But the object of the exercise here, if you pardon the pun, is not for you to get intimately familiar with the nooks and crannies of this system. It's for you to understand sort of how one does object-oriented programming. So I'd rather focus our attention as much as possible on kind of mainstream things to do rather than peculiar things to do. Okay? All right, let me move ahead. We're actually going very slowly here, so I'm going to, where'd my cursor go? There it is. Element of V. So here's the doubler class. Let me make one. I'm going to say ask D, quote, say, quote, hello. It says, hello, hello. The only purpose of this example is to show you that ask can take extra arguments. And what those extra arguments do is they correspond to formal parameters in the method. So this is the first time we've seen a method with a formal parameter. It works just like formal parameters of any procedure. So stuff has the value of this expression, which is the word hello. This isn't a very interesting object. In particular, there's no reason to ever make more than one of it because it has no local state. So one doubler is exactly like another doubler. This is a kind of functional object. And the doubling happens because of what's in the body, where you say sentence, stuff, stuff. Okay? Everybody with me? All right. Okay. So here I'm redefining the counter class. So let me go ahead and define G4, instantiate counter, define C5, instantiate counter, ask C4 quote next. So it seems to be giving the same number twice every time we call next. And now I'm going to ask C5 next. And you'll see what the two numbers are all about. The first one is specific to each counter. Each individual counter starts at 1. The second one is a count of all the times any counter has counted. So if I go back to C4, I get 6, which is the number after this 5, and I get 7. There's been 7 nexts on all counters altogether. Okay? And what's new to make that work is this class vars. So class variable is an idea. And class vars is the clause that implements it. Class vars looks just like instance vars, which looks like the first half of a let, except that the meaning is different. Namely, there's one variable total, which is created as soon as I do the define class. Instance vars are created when I call instantiate. So every time I say instantiate counter, I get a new count. But total, there's only one total. It belongs to the entire class. It's not a global variable. If I say total, it says unbound at the scheme prompt. But it belongs to the class, and each member of the class can use it. Okay? So this is good for situations where you want to keep track of something in common to every instance of a class. It's a useful idea. I can ask a particular counter for the value of total. I can also ask the class for the value of total. So you see now that classes accept messages just the same as instances do, not the same messages. I can't say ask counter next. It will give me bad message to class next. An error message, but I can ask it total because that's something that is shared by all the instances. Okay? Oops. Okay, so moving on. Define BH. Instantiate person, quote, Brian. Okay, so there's a person class, and there's 3 methods for the person class. So I can ask BH, say, I love scheme. And it does. That's not very interesting. The method is just stuff. Right? Say stuff, stuff. I can say ask BH, quote, ask. Notice it's a complete coincidence that the name of this procedure to get objects to do things is the same as a message in this particular object class. Nothing to do with each other. Ask BH, quote, ask, study for the midterm. And it will say, would you please study for the midterm? Because it uses self, which goes in some list someplace, over here. Self is a kind of hidden instance variable that every instance has, whose value is that instance itself. So the ask method doesn't just return, would you please stuff. It asks itself to say that. And that's going to become important in just a moment. And then the final one is greet. I can say ask BH, quote, greet. No argument. And it says, hello, my name is Brian. Just a note in passing, what's the name of this instance? Tricky question, right? It has 2 names. One of its names is BH, which is the name of a variable whose value is that object. And that's the name we use to get at this object from the outside. And then it has an instantiation variable name that's kind of its internal name. And that's the one that it knows about. It has no idea, as usual in Scheme, it has no idea that there's a variable whose value is itself, other than self. It doesn't know anything about the variable BH, which is a global variable, not an instance variable or class variable. But it does know that its name is Brian. So these particular objects have internal names and external names. And I'm emphasizing this, even though it's not very interesting intellectually, because when you work on Programming Project 3, the adventure game, which is coming up, your objects will all have both kinds of names. And I want you not to get confused about that. Okay. Now for the fun part in 3 minutes. Define PP, instantiate, stands for Porky Pig, Pigger, quote, Porky. Now, what does a pigger do? Well, it has a say method. And its say method basically says, call the piggle method on every word of my input. If the input is a word, just call piggle on it. Otherwise, map calling piggle over it if it's a list of words, a sentence. It really should say every. That's a boo-boo. So I can say, ask PP, quote, say, quote, I love the Beatles. And it will say, I of lei the Beatles bay. Who doesn't speak Pig Latin? Anybody? Few people. How Pig Latin, well, you know how Pig Latin works. We did it in the first week. Go back to lab 1 to review Pig Latin. Never mind. Forget I asked. Okay, so that's how its say method works. Now, notice it does not have, in this class definition, an ask method or a greet method. Nevertheless, I can say ask pp, quote, ask, play more Beatles music. It says, udwe uye is play, a play, or may, Beatles bay, music may. All right? How does it do that? It does that because of this clause. So we have a new kind of clause, which is parent. And that's a technical term also. This has to do with the question of inheritance, which is the third leg on which object-oriented programming rests. And this says a pigger is exactly like a person, except for the methods defined here. So persons don't have a piggle method, so only piggers know how to do that. Persons do have a say method, but we don't use it. We use this different say method that speaks in Pig Latin, right? So what about ask? Well, if we back up just a bit, here's the ask method for people. It says, ask myself to say this. Remember when you saw this originally for people, you thought, huh? You know, this is, why go through this effort of asking myself to say when say just returns its argument without doing anything? Now you see why. When a pigger gets an ask message, it uses its parent's ask method. But inside that method, self is a pigger. So if I ask myself to say something, it says it in Pig Latin. Okay? Pretty cool, huh? We're out of time, so I'm not going to take questions now. I just want to show you the problem, which is ask pp, quote, greet. So we want it to say, hello, my name is, and nothing happens. It's in an infinite loop. Why? Because we have a very primitive idea of what a vowel is, and so the word my doesn't have any, and so this thing is buzzing around trying to convert my to Pig Latin. And we'll solve that problem on Wednesday.